Alright students, so we're looking at our second calcmetic lesson on integrals, and here we're going to follow Callie in her New Year's resolution to exercise more and lead a healthier life. In January she purchases a gym membership and starts tracking her workouts. When Callie is on the elliptical, the rate at which she burns calories, measured in calories per minute, is given by f of t, whose graph is shown below. And so keep in mind what our units are in terms of. This may become helpful later. During the first 4 minutes, Callie burns 20 calories. So you can see the function that models Callie's calorie burning counts during the first, looks like 24 minutes of her workout. So how many calories has Callie burned on the elliptical after 16 minutes? Show work. Well, we know that she's burned 20 calories in those first 4 minutes. And then if we look at the graph, let's go ahead and kind of mark this graph up a little bit. So we know she's burned 20 calories here. And then if we create a rectangle, I think we've got a good idea. The width here is 8 times a height of 9. So we've got 8 times 9 calories. That'll be what, 72. We'll look at that in a second. And then, of course, we're looking at the first 16 minutes here. So now we've got a trapezoid. Well, thankfully, we're really good at using our trapezoidal rule. The base here of the trapezoid is 9 units, and then we've got a base here of 15. We'll divide that by 2 and multiply by the height, if you will, of this trapezoid, or the distance between these two x values. And that's 4 minutes. So that's going to be 9 plus 15. B1 plus B2 divided by 2 times, of course, this distance along the t-axis, which is 4 units. All right. Well, if you plug all that into the calculator, you get 140 calories that Callie has burned in her first 16 minutes on the elliptical. And what have we modeled there? Let's think about what we've modeled. We've actually taken the integral from 0 to 16 of f of t dt, and we broke it down into different pieces. Well, we broke it down into a piece of 0 to 12, so we broke it down into an integral from 0 to 12 f of t dt, and then summed that with the integral from, what was that, 12 to 16, I think, was the trapezoid that we created, of f of t dt. So you're looking at a sum rule for integrals. Integrals sum the way we think they would. We can just sum the integrals from different independent values, or x or t values, and just starting, say for instance, at 0 to 12, and then we can start the next one from 12 to whatever, and we can add these integrals together to get our sum total, here in this case 140 calories. After 12 minutes, Callie looks at her Fitbit and sees she's burned 1,650 calories so far that day. Write an equation j of x that gives Callie's total daily calorie burn after being on the elliptical for x minutes. Well, j of x is just going to be the integral, and excuse me, we're going to start with that 1,650, but then it's the integral from 12, so she's already burned calories for 12 minutes, to x, however many more minutes she goes, of f of t dt. So we've got the initial calorie burn in the first 12 minutes, and then the sum from 12 to whatever of f of t dt. That together will give us the total daily calorie burn after being on the elliptical for x minutes. Now, what would j of t represent in this scenario? Well, that would be her daily calorie burn before beginning the workout. So that would be the daily calorie burn before the workout, okay? Now you say, well, how would we figure that out? Well, we'd start with the 1,650, and then we would subtract, okay, 72 and 20. We'd subtract the calories before, or excuse me, what she burned during the workout. So looks like her daily calorie burn before the workout was 1,558 calories. All right, and that gives us another picture of integrals here, another rule, if you will, that we've got the integral from 12 to 0 of f of t dt is actually the same thing as the opposite of the integral from 0 to 12 f of t dt. And in case you're wondering where I got this 72 and this 20 from, these are the integrals, the calorie sum totals from 0 to 4 minutes, and then of course from 4 to 12 minutes. Okay, so these are the values we got earlier. We're subtracting those from the 1650, and that gives us the number of calories she burned before she actually started this workout. Now, after changing the settings on the elliptical, it's possible to burn calories at a rate of f of t plus 5 calories per minute. How many calories are burned after being on the elliptical for 16 minutes? And how do you know? Well, we start with the 140 that we know we burned earlier, and then we add 5 times 16, because we've added this constant to our rate of change. So not only have we burned the 140 calories, but we've also burned an extra 5 every minute. So 5 times 16, you put that together, that's 140 plus 80, so that's 220 calories that have been burned in that 16-minute period. So we've got part A here that we calculated earlier, and then we've got the 5 calorie a minute additional rate of change multiplied by 16 minutes. And you kind of look at your unit analysis here. You eliminate the minutes, and it's the 5 calories times 16 added to the 140 calories we got earlier, and that gives you your total calories. And I'm just going to abbreviate here, burned after 16 minutes. 16 minutes. All right, and that gives us a nice, another nice rule here, or another nice concept with integrals. We've got the integral from 0 to 16, f of t dt. That didn't work out too well. Let's see if we can fix that real quickly. There we go. We'll start over there. So f of t dt plus what? Plus the integral from 0 to 16 of 5 dt. We'll discuss this a little bit more later, but we've got our original integral plus this extra 5 added on to each minute. Okay, so our rate of change had changed in that moment, those first 16 minutes. Now, males burn calories approximately 16% faster than females. Their rate of calorie burn on the same elliptical is given by 1.16 times f of t. How many calories will a male burn after a 24-minute elliptical workout? Well, let's think about what's going on there. Males are burning calories 16% faster, so multiplying by 1.16 times the value we had earlier, 140, now plus some new values. So let's go back up to our graph, because we're going all the way to 24 minutes now. So we've got 140 calories from here to here. So we've already said this is 140 calories burned. Now we've got another rectangle. The height there is 15. The distance between these two is what, 4 minutes. So that's going to be 4 times 15. We'll bring that on down. So plus 4 times 15 plus, well, we got another trapezoid. So I think if you go up to the top, we got oops, let's see what's going on there. We've got something crazy going. Let's pause. All right, I think things are fixed now. So base of 15 here, and then we draw this here. We got a base of 3, and then another sort of time interval change of 4 minutes. So 15 plus 3 divided by 2 times 4, just using that trapezoidal rule. That's coming in handy, as you can see. Make sure you understand that trapezoidal rule It is a lifesaver. All right, so we've got that guy there. Well, you throw all that into the calculator. You've got 1.16 times, I believe it's 236, which gives me approximately 273.76 calories. And so what have we got going on here? Well, we've got the integral. Think about this sort of theoretically and conceptually at the same time. The integral from 0 to 24 of 1.16 times f of t dt. Well, guess what? That's the same thing as 1.16 times the integral. This is sort of our constant rule, if you will. When we multiply an integral by a constant, we just drag that constant on out front, compute the integral, and then multiply by the constant. We're computing the integral inside here. Why? Is this the area under the curve? Remember, an integral is the area under the curve. Okay? And then we multiply by our constant right there. And we get approximately 273. A moment of dyslexia there. So 273.76 calories. All right, double check me on that one, but I'm pretty sure we're good. 273.76 calories. So go ahead and pause the video here and write down your integral properties, your integral rules. You see them there for different scenarios. We've got the integral from a to c is equal to the integral from a to b plus the integral from b to c. We've got the integral from b to a, excuse me, is the same as the negation, the opposite of the integral from a to b. We've got the sum and difference rules, where we can add and subtract our integrals. We have the constant rule, where we can pull that constant on out, compute the integral, and then multiply by our constant. And then also one other big one, put a little star here, is anytime we take the integral from a to a, 0 to 0, 10 to 10, whatever, we get 0. Okay, the area under the curve at any point in time is 0. So go ahead and make sure you review these, understand these, and then check your understanding down here below, and we'll go over these together in class. Thank you so much.